just something that we did not have time to cover. First one is plotting we did trajectory generation, but we did it in joint space. Let's do it in Cartesian space. So we'll take an example of a 3-degree of freedom manipulator. So we'll do, we did trajectory generation. Trajectory generation is different from plotting the end effector trajectory. So what we'll do is, we did trajectory generation. Right? This can either be a cubic trajectory or a quintic trajectory. Right? This is 3rd degree polynomial, this is a 5th degree polynomial. So this will generate an array of Q values that you can give to the manipulator, and then you will get X, Y, Z, right? So what we'll do is we'll try to plot this to see how the manipulator moves. I'm not going to use a cubic or quintic trajectory, but I'll use a linearly time-space trajectory. So let's take a simple manipulator. We'll load in, we'll not set up a new manipulator, but we'll take one from the library. So let's use a model file. I'm just going to go here and say MDL underscore planar 3. So this is a 3-degree of freedom planar manipulator, right? MDL is a model file. So here, when I type P3, I should get the DH table for the manipulator here, right? So MDL, right? And then you just type in P3. So here in the workspace, you'll see the parameters that are loaded from the model file, okay? Fine. Let's just use a new script here. We'll write a new script. Okay. Now, what I'll do here is I'll set up two variables. First one is QZ, which is all zeros. We're starting from 0, 0, 0. This is my start position. Okay. This is the starting position, and let's say I want to stop. I'm going to call it as Q0 and QF. So this will be, let's say I want to go till pi 2π/3, and I want to go to, let's say, -π/2. All right. Now I want to space this out from 0 to, I'll generate a time vector. I'll call this as t. My time vector t will be from, so this is a linearly spaced time vector from 0 to 3 seconds, and I want to divide this in 100 points. Okay, this is my linearly spaced time vector. Now over this time vector, I want to generate a trajectory. So I want to go from Q0 to QF in a span of 3 seconds, and going through all the via points, which are 100 via points defined by the time vector there. So based on this time vector, we need to generate a trajectory. You can use this model, which is generate a polynomial here and feed in that time vector to get Q. But what I'll do is I'll use a different method. There is an inbuilt command which is J trajectory. So this is, there is an inbuilt command in MATLAB toolbox, the robotics toolbox, which is J TRAJ, which is generating a trajectory, joint trajectory. What it will do is, it will generate a joint trajectory like this. So it will give you Q, QD, QDD, and this will be J trajectory, Q0, QF, and T. You can give in more parameters, as many as you want, but this is the functional prototype. This is joint trajectory, starting joint position, stopping position, your time vector. It will retain the Q vector, velocity vector. QD is Q dot, QDD is your acceleration. Okay? We are not going to use these two because we are not trying to see how fast it moves, but we are trying to plot the X, Y, and Z. So we need this right now. We don't need these two. Anyways, so if you want to look up the complete syntax, you can go here and just type in help J trajectory, joint trajectory, and you'll see how to use this. Okay? Just type in help J trajectory and you can see the complete functional prototype. Okay. What we'll do here is we'll just use Q. We don't need everything else, which is QD and QDD. If you want to grab all three, you can just specify this in a matrix like this. If I only write Q, it will pick only the first vector that it returns. So what I'm going to do is, I'm just going to say J trajectory. Starting is Q0, stopping at QF, and I have my time vector T. If you want here, you can also give the starting velocity and stop velocity. QD0 is your starting. QD is Q dot, which is the differential of the rate of change of the joint position, which is QD0, and this is the stopping velocity. But we are not doing that, so I'm just going to stop here. Alternatively, you can also give it 0, 0, right? But it's not necessary, so I'm not even taking in the values QD and QD dot because we're not going to use them. These two I'm not even bothered about. Okay, so this will give me a joint trajectory over T, over the time vector T. Okay. All right. So what I want to do is just select this, highlight this, and say evaluate section. Okay. So long. Oh, I'm sorry. Unless you have evaluated this, it will not. So select this like this and say evaluate selection, and that will evaluate the piece of code that is mentioned here, and you will see the vector right there on your. Actually, okay, I have to give Q because there is a output suppression. So this will give you 100 points in Q. So you can always say size of Q to see the dimensions of this array. (100 rows, 3 columns for the 3 joints). Okay. All right. Now, if I apply this to a manipulator, I want to see how the manipulator moves in 3-dimensional space. So what we'll do is we'll say for all right. Now you saw that the array has the following, right? We have a set of values like this. I want to give, let's say, Q1, Q2, Q3 to the manipulator and find the position. How do I do that? How do I find the position for a given set of joint angles? Inverse will give you Q. Forward kinematics. Now, to do forward kinematics, we can multiply the 3 A matrices, right? A1, A2, A3, and get the first 3 elements of the 4th column, right? So if you have this, you will generate a T matrix. T will be equal to A1, A2, A3, because this is a 3 degree of freedom manipulator. Here you will get R3 by 3, X, Y, Z, 0, 0, 0, 1. So this will give you the position of the end effector. However, we don't want to do this. We'll just run through this a command which is fkind. Fkind is your forward kinematics. Okay. So if you don't want to multiply these, what you'll do is you'll use the just like you have a toolbox function like this. For forward kinematics, we have a command called the fkind. Forward kinematics. Here you'll give the robot object and Q, the joint vector. This will return the T matrix. So the output of this is a T matrix. So for example, I can say that my here, let's say, let me go here and do a sample command. So the name of the manipulator here is P3 because it's a 3 degree of freedom planar manipulator. So we'll use fkind over this. There are two ways to write this. First one, you can write it like this. P3, comma, Q, right? Q can be anything. For example, I'm just going to use 0. For now, I'm going to use 0, 0, 0. Or you can give it as anything else. And it will give you a T matrix like this. Or I can write it like this. As a property of the manipulator. Okay. So either of these, fkind, you give the robot object and Q, or you can write it like this. This will return the same thing. Alright, so let's use this. I'm going to say T will be equal to so we'll go row by row. This is your forward kinematics. Okay. Now we actually want to plot this manipulator like that. So what I'll do is I'll say here, first we will extract this point and we'll say plot P3, comma okay. This is plotting the manipulator pose. Okay, and now what we'll do is we'll plot the end effector point. So we'll use a three-dimensional plot, plot 3. Plot 3 plots a three-dimensional plot. If you use just plot, it's 2D. So here we'll say Q of, T. First row, fourth column, comma, T of second row, fourth column, and I'm going to say this will plot plotting the end effector position. And here we need to mention, because we are trying to hold on to this plot, we'll mention hold on. After you plot the manipulator, just mention the additional property, hold on, so that it holds on to the figure. And here, we'll go back and we'll say N. All right. So let's run this. Okay, forward kinematics, undefined function. Okay, so let's go here because we cleared everything. It lost the model file, so planar 3. Just put this in and we are all set. Okay, this is loading the model file. Okay. Include MDL underscore planar 3, that will load the model file. So you'll see how the trajectory is being plotted by the manipulator. In this case, however, okay, so you can see the end effector trajectory. Previously we were plotting the joint angles, right? When we did a trajectory generation, we were plotting the 3 joint angles. In this case, you will visualize how the end effector will move in this case.
Can you go back to the code?
They are good there. Hold on. Include hold on. Here, if you don't include hold on, you either get rid of the previous plot. Go here and make sure that you have this. All right. Because if you don't, just remove it and see, it will only plot the current point where the manipulator is. It won't remember the previous point where it was. Okay, so you can change the trajectory and you'll see, I mean, this is a very simplistic manipulator, but if you have a complex one, you can actually see how the trajectory works. This is not a cubic or a quintic trajectory. This is a linearly spaced, time-based trajectory. But for your own model that you generate, the previous ones that we did, cubic and quintic polynomial, the trajectory will not be as smooth as this. You will have like a different curve. This is a very symmetric one. Okay. Let's do one more thing. Let's load this. I'm going to give this out. I want to do we did the position. From this, we want to generate from the R matrix, we want to generate the Euler angles and the RPY angles. So let's do that. Let's pass this around. I'm going to do the first manipulator and I will require you to work with me to do the second one. So in this case, we'll just list out what we need to do here. First, you'll define the DH of the manipulator. Define the manipulator by its DH. Okay. Second, you'll have to generate the transformation matrix total transformation T0n. Finally, you will find forward kinematics. Okay, and here you'll find Euler and RBY angles. Okay, Euler and RBY angles for the end effector orientation. So let's start by doing the first step. Define the manipulator. Let's create a DH table based on for the Stanford manipulator. Let's generate the DH table and we'll do the rest one by one. Let's create a new script. Right? So we'll say define link by link L1, L2, L3. This is a revolute joint, so you'll give sigma 0. I'm not sure if this version. There is stan F here.
Stan F?
Yeah. Just type in stan F. MDL underscore stan F. That's probably the version 10. Okay, but anyways, type in help, there should be one, I think there should be one, just type in help. Help, robots. Yeah, now check the model files. You'll find one, there should be one sample. Yeah, just go there, that's fine. But this one will be different, the joint lengths will be different, that's fine. Okay. So this is a configuration with a wrist, so you'll have 6 degrees, and we'll judge the orientation of the wrist based on the RPY and the Euler angles we find out. Okay. Now it's good practice because there is one prismatic joint here to give the Q limb so that we can actually define the limitations on the joint right here, just in case if we need to plot that. So L3.Q limb, let's give it as 0 to 5. Okay, so this is your joint limit on the prismatic joint. And now we can define the manipulator. We'll call it as span will be equal to serial link Okay, so here what I can, let's look at the configuration. Let's run this once and see if there is any issues with that. I'm just going to call it as angles. Okay, so we have the DH here. So that's clean. Now, the next step that we have to do is to define the generate the transformation matrix T. Now, what we'll do is, to generate a transformation matrix, we need to know the posture. So let's define Q here. Okay, let's define Q. Q is this. I'm going to pick the first. The Q is given to you here, so I'm going to use this Q. Okay. Now that is all in degrees. So this is 60, right? 93. 45, 60, and 30 degrees. So this is in degrees. I want this to be, I cannot give it to the manipulator in degrees, I have to convert that into radians. Except this one, because this is a link, this is not an angle. right? Except the middle one. If I convert the whole thing into radians, then that will change the dimensions or the displacement of that joint. So what we'll have to do is, unfortunately here, we'll have to do this element wise to convert this into radians. So pi by 180, we'll multiply this with everything except, what I'm going to do is, let's do this. Control C. I'm going to call this as a constant K. And we'll just multiply this by K so that it is alright. This will change the whole thing into radians except the third link. Alright, now there are two ways to get the T matrix. The first one is exactly what we did in the previous example, which is the following. Okay, now we'll do the, I'm just going to create a new section here, which is so the first one, what we can do is we can directly give T as like this, F prime of stan of Q. Let's check if we get our output. I'm just going to run this here. So you get your T matrix directly. Okay. If you want to do it using a toolbox command, this is using the using the toolbox function. If I don't want to use this, how do I generate the T matrix? We have to multiply A1 to A6 in this case, right? Because it's a 6D of manipulator. Alternatively, I'm just going to comment this. Okay. The second method to do is using the toolbox. So I'll go for I is equals to 1 to stan dot n is the number of links in the manipulator, right? Dot n will give you the number of links in that manipulator, and we'll say here, and I'm just going to start off with the empty matrix in T. T is equal to I4. This is a 4x4 identity matrix. Okay. And